All right, so a lot of you might have seen Dr. Jackson's presentation yesterday. He was talking about the front end of this mission. I'm talking about the back end, but for anybody who missed it, I'm going to go over it as fast as I can. So essentially, we see, there we go. This is our propulsion device. This is going to get us to Proxima B and get us into orbit. But then we have to do something. Since this is a propulsion device, we got to kind of close it up so that we don't just skim off the surface or go into the atmosphere and burn up. So the way that we're going to achieve this is we're going to turn these into spheres, and then that's how we're going to generate power. Still the same thing, we're using fusion as our power source, and we're going to get into that right now. So again, same reactor structure that you might have seen a little bit yesterday, but I'm going to go over it again. We see this electrostatic potential well. We got one MeV here in the center and ground at the end. And the really cool thing about this architecture is it's self-cleaning. It's kind of like an oven on self-cleaning mode. Hopefully it smells better though. I don't know. Those always smell really bad. But the idea is when we got our fusion reactor we're using here is a Proton on lithium-6. When those two get close enough to fuse, they also get close enough for Coulomb scattering, which creates a big messy cloud in the middle. And that's going to not give us break-even operations, which is the whole point. We're trying to get energy out of this so that we can power the ship and, take pictures and communicate back on Earth. That's the whole point. So we have to be able to clear out that cloud, and the beauty of this being an electrostatic trap is that we're able to clear out all of that junk that gets stuck in there. So more about the Proton lithium-6. So here's the equation. You get proton lithium-6 comes out, a helium-3 and a helium-4. And here's our graph of it. So we got the kinetic energy and the cross-section. And this is assuming where we have the lithium-6 is stationary and we have a proton going and hitting it. And our resultant cross-section, we get a peak here around like 1900 keV. And that's going to be a cross-section of 0.2. For reference, DD is at about 0.1. So as long as we're above 0.1, we're looking pretty darn good. So now we see, okay, what kinetic energy do we want to run it at? Well, remember, with the whole electrostatic trap, the point is we have equal and opposite momentum coming in, equal and opposite momentum going out. So that's a little different from the graph that we saw. So we're going to figure out that about 1100 keV for the proton and 200 keV is going to get us that equal and opposite momentum. So we got the proton and the lithium-6 coming into the center. And if we do some math, we figure out that's about like 1600 keV on this scale. So 1600, and we see, sorry, there we go. That's at about 0.17, 0.18. We're good. Now, I'm an engineer, and I'm thinking, well, why don't you just turn it up a little bit and we hit the max? That would make sense. You get more reactions out of that, right? But this is a little bit more than just an engineering optimization problem. So again, I said coming out is equal and opposite momentum because we have to obey the laws of physics. So we have a helium-4 and a helium-3 coming out. Helium-4 is going to go slower. So helium-4 shoots out of that electrostatic trap. Oh, sorry. Shoots out, gets out of the inner sphere that we had, and gets all the way to the edge of the outer sphere. It's slowed down by the electric field between those two spheres, and it comes and it just barely stops on that outer sphere that you saw on the first slide. And then you have the helium-3, that one's lighter, so it's going to be going a lot faster. It's going to come out of the electrostatic trap. It's going to get slowed down a little bit by the field between the two spheres, and it's going to whack the outer sphere. And we figure out that it's going to have about 755 keV, and it's going to go about 2 microns thick. And we're thinking, okay, so we need the outer sphere to be about 2 microns. So we have one parameter set there. 2 microns is not too bad, like the solar sail that was passed around earlier. We heard that one was about 2 microns. So that works out. So next thing, how is it actually being converted into electrical power? And I like to say, this isn't good for anybody who wants to get funding, but it's basically a really, really expensive capacitor. Really fancy, expensive capacitor. The lithium-6 comes out of the ion sources, charges, and then the helium-3, helium-4 comes out and whacks that outer sphere. So you got the positive terminal as the outer shell, negative terminal as the ion source. And essentially, we charge up, and that is how we can power the spacecraft. Communications, pictures, you name it, whatever is necessary for this mission. And then also of relevance, we need the proton current to be around 170 milliamps. And we sit here and we go back and we remember the voltage drop is like a megavolt. You don't need that to run this spacecraft. You needed it to get out there, but now you're sitting there and you're not doing a ton. Again, you're taking pictures, you're running some calculations, and you're sending some data back to Earth. You really only need about 100 volts, not a megavolt. So how do we step down all of this voltage? So that was our next question. And really, there's a lot of options. You can look online. My coworker has worked a lot. He picked the klystron to look at first. He's an electrical engineer, so that is his realm. I'm mechanical. So if you are really big into all these transformer concepts, I would recommend you go look at his work. It's very good. But of course, there's other options to look at. We could go just for a steam generator, motors, shafts. You could do fiber optics, or you could just do a bunch of like traditional transformers. There's a lot of options, but we just wanted to touch on that. That is not what our experiment is about. But again, big concept. So, getting into what our experiment is looking to answer, and that's electric field emission. And the first thing I want to direct you to is these two drawings here. You can't see it, but there's these little blue dots. I promise they're there. And the little blue dots represent wires. And you see here, I counted out, there's 36 wires here. That was really fun to count. It's really small. And these have 12 wires. But if you see, as soon as you get away from the little wire dots there, these two fields really look the same. The equipotential lines, they're really, really similar. So we're seeing for a fixed wire diameter, so we're assuming these two have the same size of wires. As the number of wires goes down, we're not seeing a big change in the electric field shape. The only change is the opacity of the wires, which is going to become important because remember, you're having all of your fusion products go through these wires, and you don't want them to hit because not only is that going to degrade your wires, it's also going to, it's going to lower the amount of energy you can actually produce, the amount of power you can get out of this. So you really want to have as few wires as possible so that you don't have those interactions. Plus, as you have less wires, you're making your whole spacecraft lighter, which is nice. So this was the big question we wanted to answer with our experiment. Is how can we optimize all of this? Let's look at the electric field. So before we get into the experiment, there were a couple things we were checking on with the outer sphere. You're not going to hear any more about the outer sphere after this. So one thing is the outer electrode temperature. So P net represented by the heat that's essentially deposited into that outer electrode due to the bombardment from the helium-3s. We plug that in. We set T naught, that's essentially temperature space. We'll just say that's 0. And then we want to see what T here is. T to the 4, that's our equilibrium temperature for that outer electrode. So we plug in some parameters. We're going to say the radius of that outer shell is about 1.5 meters. And then we grab that proton current we had before, 170 milliamps. And then the helium-3 collisions we're getting at about 250 kilowatts. We plug all that in and do all that fun math, and we get about 900 Kelvin as our equilibrium temperature. And that's way below the melting point of, say, titanium. So if we were to use titanium, we're all good. And that is also the material we used when we were calculating how deep the helium-3 would penetrate, again, that 2 microns. So assuming we use titanium, we are all good on the temperature front. And then the one other thing is, how are we maintaining this shape? When we were talking about this as a propulsion structure, it was like a self-inflating sailboat is how I told people about it. I'm like, yeah, it's a propulsion structure. It's like a sailboat that makes its own wind. And that's a really fun way to explain it. But now we have two spheres, and they're oppositely charged, so they want to go towards each other. And before, our biggest problem had been, how do we get that outer sail to not collapse into the inner one? Well, turns out when we were experimenting, the inner sphere was more of the problem. And one problem there was the inner sphere wanting to repel against itself. So if you see there's a little epoxy right there preventing the wires from popping out and, exploding. Again, explosions in space, not a good thing. But another big thing is those outer wires being attracted to the inner wires being attracted to that outer shell. So there's two ways that we can keep these two shells separate. And one is there's a minimum flux from those helium nuclei that's going to produce enough force on that outer one to keep it inflated. That's an option, some minimum flux, and it's applying a force on the outer sphere, and that's going to keep it inflated. Alternately, we could also just spin the entire thing, and that'll provide the centrifugal force that's going to keep the outer sphere inflated. Or it can be some combination of the both. That's all that we've done on that so far, so we're going to get back to the experiment that we have recently run. See, I promised there was a wire at the middle of these. So there's your wire, the gray surrounded by blue. This is a zoom in of some of the equipotential lines I showed you a few slides back. And basically what we're seeing here is as we reduce the radius of the wire, here in this equation, we reduce the size of the wire, electric field goes up. So we're going to run, I think there's 5 tests that you're going to see in a few slides of different radius, wires of different radii, and number of wires. So we're going to see how we can play with the mesh opacity there and get electric field emissions. And we're also going to see there's a few other conditions that we were keeping track of during this, the temperature of the wires, the temperature of the surroundings, of course. And again, remember we did all of this experimentation on Earth, so there's some things that don't line up because we are constrained by gravity here. So the first thing that I want to bring up, this is a picture of the outside shell. So I lied a little bit. There's the last you'll hear of the outside shell. We're just concerned about this inside. So this is the first test we ran, and these are pretty chunky wires, if you can't tell. They're about 1/8 of an inch thick. And you're going to see there's really nothing holding it up. You have the bottom here where they're all connected. In the middle here, going down like the central axis, every other test we ran, we had to add like a beam to support it, or else the other wires, they were so skinny that this bottom part that they're connected to would pull them all down, and then we didn't have a sphere, we had like an ellipsoid looking thing. So just keep that in mind. For the first one, there's no axial stick, and the rest of them do have one. So that's shown in this drawing here. We have the small field made by that stick. But again, going over this, you can see here, it's a little bit of a better picture. We had to put some epoxy here, or else these wires had such a big force on each other that they were just popping out. They weren't strong enough to stay formed. Like these thicker ones, they're stuck in there. But the smaller ones, they were wanting to pop out. And again, stainless steel wires, the eighth inch thick ones were just a lot stronger and more well formed into that shape. So now here is a graph that was produced through the Poisson program. And really the part that is notable for the interstellar part of this, for the space travel, is to the right. Because we're looking at this is the radius by electrostatic potential. All of these really small radii, this is where the reaction is happening. That's that electrostatic trap. So it's not as big of a deal. You're not going to see the helium-3 nuclei getting affected here. This is the part that we want to look at. So it's really hard to see the theoretical solid, and that's the calculation based on a solid inner sphere and a solid outer sphere. Obviously, you can't do that because nothing would escape the solid inner sphere. But you could see it's a green line. You can see it start right there, and then it goes like that. But really, all of them are following it very closely. So we look at the like no stem and 5 wires, the stem and 8 wires, those lower mesh opacities. We're seeing they do follow the theoretical pretty closely. Coming up is going to be the details from the actual experiment, and I will note the amount of wires is slightly different, and that's because Poisson runs its calculations like as lines of latitude, whereas we ran our experiment with lines of longitude because it's far easier to set it up that way, again, with the little connecting bit at the bottom and then hang it from the top. It's pretty hard to suspend a wire in midair. I don't think that's going to happen. So we had to adjust that a little bit to make the math line up. So you see stem in 5, 8, and 17 wires. The figures are a little different on the next table, but it's the same idea. So here it is. We see the maximum voltage we were able to put through is 42 kilovolts. That was just a constraint of the instrumentation we had. And we see we started with those really chunky wires of about an 1/8 inch diameter. We started with 16 of them. And then we moved the wire size down until we saw a different voltage, a different max voltage. And that took until we were at 10 mil thick wires. So those really tiny ones that kept popping out. Took, I don't know how many tries to get that right until they stopped popping out. But yeah, we finally get that change here to 28 kilovolts when we have the sphere diameter at 8.5 inches, we have 18 wires and 10 mil thick wires. So just wrapping up, and I'll have time for questions after this, I think. But from this experiment, we found the conditions that we need for electron field emission, what we need those wires to look like, how many and how thick. And we can start to look at how that mesh opacity is going to affect the power that we generate. Okay, again, this is all in theory, so there's 100 questions that you might be able to ask, and the correct answer will be, I don't know. This is just the questions we chose to explore this time around. So now we know how we can generate some power enough to get all the stuff that would be needed for this mission and make this a very useful mission to Proxima b.